First, let's discuss control charts for continuous output measurements. For these types of variables, we are primarily interested in two different charts. First is the X-bar, or the mean chart, which helps us control the central tendency of the process. And second is the R, or the range chart, which helps us control the dispersion of the process. X-bar and R charts should always be used together, allowing us to see both the dispersion and the central tendency side by side. For the X-bar charts, we encounter two different situations. The first is when we know sigma, that's the population standard deviation. In this case, the target value, or center line, is X-bar bar. The upper control chart limit is the target line plus Z times the standard deviation of the sample means. Here, Z represents the Z-score. Typical values of Z include 3 and 2. The lower control limit is calculated similarly by subtracting Z times the standard deviation of the sample means from X-bar bar. Notice that the limits are symmetrical around the target value. In this example, we are sampling 9 cereal boxes each hour from the filling line. In the first hour, the first box we sample and weigh is 17 ounces. The second box we sample weighs 13 ounces, etc. After we've collected the weights, collected and weighed the entire sample for the first hour, 9 boxes, we calculate the sample statistic, the mean weight. In this case, it is 16.1 ounces. So if you average those 9 values that you see, you will get 16.1. We continue to sample the filling line for each hour for 12 hours. The sample means for those 12 hours are shown in this right-hand side table. In this particular example, we know the process standard deviation, sigma, and it's 1 ounce. We then use these sample statistics, the known sigma, and a z-value of 3 to compute the control chart limits. In this case, we end up with nice whole numbers of 17 ounces for the upper limit and 15 ounces for the lower limit. Using these limits, we are interested in determining if the process is in or out of control. So to create the chart, we first draw the established target value of 16 ounces and the upper and lower limits, 15 and 17. It would be very rare that every single sample mean, one for each hour, would be exactly the same. So everything that falls between the control limits would be considered to be due to natural variation and perfectly acceptable. To visualize if the process is in or out of control, we next add along the x-axis each sample, in this case each hour, and the sample statistic that we calculated. That is, the sample mean for that hour. It is vitally important that you understand that we are looking at and plotting only the sample means, not the individual box weights. As we plot the sample means, we see that hours 10 and 11 are below the lower limit and hour 12 is above the upper limit. These points indicate that the process is out of control. In fact, all we would need is a single point outside of the limits to signal to us that the process should be investigated for possible assignable causes. Recall that an SPC chart only provides a signal that something is wrong. It allows us to take an action, the action of investigating why the process is not producing the expected output. The second way we can create X-bar charts is when we do not know sigma, the population standard deviation. Now I think it's important to take a moment here to reflect when you may encounter the two different ways of computing limits for X-bar charts. The first was when we knew the population standard deviation. So when would this occur? You might say never, because it would mean you'd have to measure every outcome of the entire population, which is probably practically impossible, or too time consuming, or too expensive. It's the whole reason we have sampling. So then, why did we talk about it? In reality, you would use the known sigma approach when you have a process that has been both in existence and stable for a long time. This would enable us to estimate the population standard deviation quite accurately. If, on the other hand, you have a process that does not have a long history, then we would probably use the unknown sigma approach. When we do not know sigma, we see that we use some control chart factors. We'll see the chart on the next slide. We use these in conjunction with R bar. R bar is simply the mean or average range over the samples. Note that this implies that we must have access to all of the individual raw data in order to calculate R bar. In our previous example of cereal boxes, we did not have all of the raw data, so we would not be able to calculate R bar. So here is the table from Supplement 6 from the textbook. It contains the control chart factors that are used to create both the X bar chart for unknown sigma and the range chart, which we'll get to in a moment. Notice that the chart factors depend upon the sample size n. This table is not all-inclusive of sample size options, but there do exist other tables out there that are more exhaustive. Again, we want to use the range chart alongside the X bar chart. The range chart will help us monitor process variability. To set the control chart limits for an R chart, we use control chart factors found in the table from the previous slide and multiply them by the average range of the samples. So let's examine why it is important to use both the mean and the range charts to monitor a process. In this first example, if we were to only use the X bar chart, then we would incorrectly assume that the process is in control. Notice that the mean is very consistent, but the variance is increasing as we pass through time. The distribution is getting wider. If we use a range chart, we would be able to identify the increase in variation and help us start the process to correct the problem. In this example, we notice that if we only use the range chart, then we would incorrectly conclude that the process is in control. The variation of the process is consistent throughout time. Looking at the mean chart, however, indicates the mean is shifting upward through time. Again, this is a bad thing and would need to be corrected. Hopefully these two examples provide you with a sense of why the mean and range chart should always be used together.